till now we have elaborated about stress and strain. The stress was the force applicable on a body which changes its dimension over the unit area or the area of the body, right? And secondly, the strain. Strain is the change in dimension upon original dimension. Now, as we have already studied about stress and strain, suppose this body, suppose this marker is acted upon by a force, a very small force, which acts for a small interval of time and then it is removed. What I just did was, our deforming force is acting on a body and it has just been removed in a small interval of time. So will this body regain its original shape and size? Yes, it will. So the thing is, the deformity of a body or not regaining the original shape and size actually depends on a particular limit of the body, which is called elastic limit of the body. So elastic limit is defined as, it is the highest value of deforming force. That deforming force which is actually, what is it doing? It is changing the dimensions of the body, right? So it is highest value of the deforming force, which when removed, after which the body regains its shape and size completely. For example, if we have a body, suppose this is a piece of sponge, okay, and a deforming force, suppose something is compressing this sponge, okay, there must be some limit after which when the force is removed, this body will again go back to its original shape and size. This is the elastic limit. So I'll define it again for once. Elastic limit is the highest value of deforming force after which, in brackets you can write, after removal of which, it is the highest limit of deforming force after removal of which the body on which the force was acted upon will completely regain its original shape and size. This is called elastic limit. There is another term called elastic after effect and elastic fatigue, which we will be learning. I'll just give you a small hint what is elastic after effect. Elastic after effect is when a body is compressed or stretched or done whatever. Suppose there is a deforming force acted on a rubber band. So when the deforming force is removed, the body regains its shape and size, but it takes some time to regain its actual shape and size completely. So that is called elastic after effect, which is the time required by a body to regain its original shape and size after the removal of deforming force. And another term is called elastic fatigue, which is the loss in elastic properties of a body after repeated stress and strain. For example, take a rubber band, stretch it, lose it, stretch it, lose it, keep doing that repeatedly. What will happen after a time? The rubber band will be loosened up, right? So you will see that initially the rubber band size was something, and after repeated stress and strain it has gone to something else. So a property of a body in which it loses its property of elasticity, that is called elastic fatigue. Now we'll study about Hooke's law. What is Hooke's law? Hooke was the scientist who gave a detailed experimentation module on elasticity, on solids and its various properties. He conducted an experiment. There was a spring. He suspended a mini tripod or mini socket sort of thing on which you can place your weight, and here this is the original length, right? Now if you keep putting up loads on it, okay, the length is going to increase. What are you doing? You are increasing the value of stress, and he drew a graph between stress and strain. Stress and strain. This experiment was conducted again after removing the spring and putting a normal metallic wire. This experiment was conducted again by removing the metallic wire and replacing it with a solid bar. So the point is, the objective of this experiment was to conduct this experiment to see a relation between stress and strain on various types of body, and just to be able to plot a graph between them, right? It was seen that stress is directly proportional to strain according to Hooke's law. So what's Hooke's definition is? Stress is directly proportional to strain, but we have a condition applied here, that small star you see, asterisk sign. The stress is directly proportional to strain only under elastic limit. After elastic limit, stress is not directly proportional to strain, because the graph goes something like that. It goes weird, okay? So till now the definition according to Hooke's law is, under elastic limit, stress is directly proportional to strain, and this is the graph which we'll be seeing. Now we know that we have studied various types of stress and various type of strain, right? If I try to find a mathematical relation out of it, I'll write stress is equal to K times strain, where K is, or here I'll write E because of elasticity, E times strain, where E is constant of proportionality, which is called either it is called by two names, either coefficient of elasticity, or it is also known as modulus of elasticity. So we have two names for this constant of proportionality, which is called, either you call it coefficient of elasticity or you call it modulus of elasticity. So basically, what is this modulus of elasticity? According to this formulation, E is equal to, or K is equal to, let's stick to K only because this is the word which we are more familiar with, stress over strain, right? What is stress? Force applied per unit area, or total force upon total area. Strain is change in dimension upon original dimension. So stress upon strain is the coefficient of elasticity or modulus of elasticity. But since we have studied various types of stress and strain, for example, we have various types of stress, longitudinal stress, shearing stress, and similarly for strain we have linear strain, volumetric strain, then shearing strain. Then according to that, if we apply various types of stress and strain, we'll get various types of coefficient of elasticity or modulus of elasticity. So there are basically three types of modulus of elasticity. This thing, the first one is called Young's modulus. Young's modulus of elasticity. Young's modulus is what? It is normal stress upon longitudinal strain. This is Young's modulus. Second, we have bulk modulus of elasticity. You have to write it complete. Bulk modulus of elasticity, that's the complete name. Now bulk modulus is again normal stress upon, instead of longitudinal strain here in bulk modulus we have volumetric strain. That means change in volume over original volume. Volumetric strain. And lastly, we have shear modulus, or there is another name for it. It's called modulus of rigidity. These are two names. In this we have tangential stress over shearing strain. Now, if I put the values of all of these, let's start with Young's modulus, normal stress over longitudinal strain. That means in this case, we are talking about a wire or a length, linear length, on which the load was applied, right? So because of this load, the length, initial length, got extended to some other length. So here, now what is the formula for normal stress? It is force upon area, and whereas longitudinal strain is change in length over original length. So this goes multiplied on the top. This implies Young's modulus is equal to FL over A delta L. So what do you think? What would be the SI unit of Young's modulus or SI unit of anything? See, we know the SI unit of stress, which is force per unit area, because stress is force per unit area. Strain is dimensionless because it is change in dimension upon original dimension. So anyhow delta L upon L is meter upon meter, it will cancel out. So strain is a dimensionless quantity. So whatever the value of SI unit of this thing, the coefficient of elasticity will be, it will be obviously be equal to the SI unit of stress. That means force upon area. So this is the whole formula of Young's modulus. Sometimes you might find that if they have given the radius of the wire or diameter of the wire, this same formula can be written as FL over what is A, pi r square delta L. You just poured in the value of A to pi r square. Then second, what is bulk modulus? Bulk modulus is represented by beta, or in some books you write it by B. Bulk modulus is normal stress, which is F upon A over volumetric stress, which is change in volume upon original volume. So this comes out to be FV over A delta V, right? Sometimes again instead of A you will write what? Pi r square. Okay, here even V is written as pi r cube or 4 by 3 pi r cube, and according to the shape of the body. So this is the whole formula for this. Lastly, shear modulus or modulus of rigidity. Tangential stress is back the same thing. It is F over A, whereas shearing strain is L over delta L upon L. But we all know that this delta L is that thing which we did that day. If this was the body and it has been acted upon by this force in this direction, so the change, right, this angle is theta, which is this delta L upon this much L. So tan theta is basically what we are talking about in case of shearing strain, because this body got tilted basically and the body has reached this part. It, instead of being straight, it just got tilted, but the volume remains same. That is what we did in case of shearing strain. It's a type of strain in which the volume remains constant but the shape changes, or the body just get tilted from one unfixed position. So the formula is still same as in the case of Young's modulus, but you have to keep that in mind that in this case the delta and L are actually what thing, right? Because here delta and L was the change in length. In here delta L is the change in position of one of the edge, right? Anyhow, this will become FL upon A delta L. This is the value of shear modulus. One more thing, bulk modulus reciprocal, which is 1 upon beta, this is called compressibility. So what is compressibility? It is a reciprocal of bulk modulus of elasticity. So these are the three types of coefficients of elasticity, which are Young's, bulk and shear modulus of elasticity. Same, all of them have same SI units, which is the SI unit of stress, that is force per unit area, which is what? Pascals. And this all has been followed by Hooke's law.